Hello everyone, I'm Yujing Liu. Today I will present a paper named 3D Hand Reconstruction from a Single Image based on Biomechanical Constraints. The authors are 龟清力、智慧屋、玉兴六、灰千章、用微涅 and 爱花茂. I will introduce the paper in the following 6 parts including background, related works, preliminaries, the proposed method, experiments, and conclusion. The first part is background. Hands play an indispensable role in human daily life. 3D hand models can be reconstructed from point clouds, from wearable sensors, and from images. And reconstruction of 3D hand geometrics has key significance in a variety of computer graphics applications, such as computer animation, 3D games, virtual reality, and augmented reality, and so on. The second part is related work. A few words make direct hand, pose, and shape reconstruction. They require precise and dense input in order to achieve high quality. Some works build a database of different 3D hand shapes and poses, as well as their different view images. Users can retrieve an approximating mesh model in the database according to image or other information. Inspired by the idea of linear blend skinning for human body, a number of parametric models are proposed to represent hand shape and pose. A more popular model is Mano by Romeo et al., which adds a set of shape parameters to the LBS model in order to capture the hand shape of different individual subjects. Many works try to reconstruct hand based on parametric models. Some make reconstruction based on inverse kinematics. They use traditional optimization and numerical solutions, which leads to huge time cost for each iteration of optimization. Recent development shows that deep neural networks are very promising to reconstruct 3D hand poses, but they ignore orientations and require additional steps. Thus, their robustness is not good enough and is still a challenging task to predict 3D joint positions with accuracy. The third part is preliminaries. For convenience of description, we first introduce the formulation of Mano, and then present the notion of hand anatomical kinematics as preliminaries. Hand model with articulated and non-rigid deformation, abbreviated as Mano, is a hand parametric model. It employs a group of PCA bases to capture the shape variation of specific hands and then employs the skeleton skinning technique to generate motion gesture of the specific hand, which means the rotation of one joint is a cumulative multiplication of 3 nodes from the root to the current node. In our setting, we neglect hand shape and only reconstruct the pose using Mano. Particularly, denote their rest pose counterparts by J star. According to the forward kinematics, this yields the following global transformation matrix for joint K. E omega I is the rotation matrix of joint I. AK represents the node path from the second level ancestor, which is adjacent to node 0 to the parent node of joint K. PI denotes the parent node of I. GK describes the transformation of joint K related to the world system. We use the anatomical kinematics structures which is also adopted by robotics arms. Such structure employs the same skeleton as shown in the figure in which hand joints are classified into hinge joints and saddle joints. Specifically, a hinge joint has one degree of freedom, namely, bombs shooting from this kind of joint can only conducts bending motion as shown in the left of the left figure. A saddle joint has 2 degrees of freedoms, which are respectively described by two different rotational angles. Biomechanical constraints are exploited to constrain the motion range of these angles. As shown in the figure on the right, its origin of joint K is placed. The x-axis points from the parent joint to itself, and the rotational axis of the bending motion around the origin is viewed as y and z axis. As let phi zk and phi yk be the rotational angle along corresponding axes, the table on the left shows the limit rotational angle of each joint. Hinge joints include joints on the top three rows of the table, and saddle joints contain joints on the bottom two rows of the table. The fourth part is our proposed method. First, constraint kinematics for hinge joint and saddle joint are listed as below. We can express the rotation matrix of hinge joint as the first formula, with nz is a unique vector along z-axis and phi zk is between phi zk min and phi zk max, where E is called Rodriguez function. For saddle joint, the motion of the bomb shooting from it is a composition of the two rotations, respectively around the z-axis and y-axis. Similarly, denoting the two angles by phi zk and phi yk separately, we then have the second formula, where ny is a unique vector along y-axis. The rotational angles satisfying the following ellipse constraint as the third formula. Remind that the rotation of one joint is a cumulative multiplication. Our objective model is shown as below. Given the estimated joint positions denoted as JE, motion estimation can then be formulated as minimizing the mean square distance between the prediction joint positions and the given ones under hand biomechanical constraints to find the global transformation RGTG and the pose parameters of Mano. We adopt block descending method for our numerical solution. We divide the variables into different blocks according to their joint number. To solve, we minimize a subproblem by fixing all other variables. Different update methods are taken in different joint solving situations, including global rigid transformation, saddle joint parameters, and hinge joint parameters. We first evaluate the mean pose of the Mano dataset as the initial pose. Then in our setting, the width joint is fixed and its global transformation is described using camera parameters instead. The global transformation in place of the root pose, hence all hand joint positions are transformed correspondingly. While only considering Rg and Tg, the optimization is formulated as below. After that, we update saddled and hinge joint parameters. Saddle joints located in the second level of kinematic chain, which are directly adjacent to the root. Updating the transformation of this kind of joints only influence the position of their descendant joints. Therefore, the optimization for joint K reduces to the below one. The pipeline of our algorithm is as follows. The input are the target position of all joints, joint rotation constraints, and stop criteria. The output are the pose parameters and camera pose. And we first initialize our pose parameters. During the optimization process, two types of variables are optimized alternatively, and this iteration will end until the criteria is satisfied. We will then show our experiments. As the wrong joint's location in the second column and the corrected joints in the fourth column, The figure shows that the biomechanical constraints can help to correct unreasonable joint locations resulted by wrong rotations. Here are some visual results of the proposed algorithm. The left of each example is the input joint positions or the input hand image. The right of each example shows the corresponding results. We also illustrate the results by Frank mocap as comparison. Each row shows 2 examples and total 8 examples are depicted. Each example includes 3 images, which are respectively the input image, the reconstructed hand model by our method, and the results by Frank mocap. Visually, the hand gesture by our method are better than that and better than those by Frank mocap. In the first example, the gesture by Frank mocap is even wrong. To show the stability of our approach, we applied it to reconstruct the sequence frame by frame. Total 100 frames are reconstructed, and we also compare it with Frank mocap. The top row shows some images of the video. The middle row shows the corresponding results reconstructed by our approach, and the bottom row shows the results by Frank mocap. We also compare our algorithm with state-of-art approaches. ProSnet is trained using the training images to estimate 3D joint position as input of our method. All involved reconstruction algorithms are directly used without additional training. The table on the left summarizes the reconstruction errors by the involved approaches, measured by a variety of error metrics, which also shows that our method outperforms the state-of-art methods in almost all indices. Although minimal hand is faster than our approach, its accuracy indices are the worst. The figure on the right depicts the percentage of correct key points curves by some approaches and ours. It can be observed that our approach performs the best. And here is a short video to demonstrate our results in 3 dimensions. We present the single frame reconstruction first. And then we present the sequential reconstructed results. Finally, we conclude our paper. We proposed an inverse kinematic framework with the biomechanical constraints for hand reconstruction from a single image. A block coordinate descent algorithm is designed to solve the parameters of joints one by one, and our approach can efficiently achieve higher quality. Thanks for your attention.